My name is Mashrur Rashik. I'm a PhD student at the University of Massachusetts Amherst, and I work in the HCI Viz Lab with Dr. Narges Mahyar and Dr. Ali Sarvghad. I will present our paper, CommunityBots, creating and evaluating a multi-agent chatbot platform for public input elicitation on behalf of my co-authors and collaborators from the University of Massachusetts Amherst. In recent years, conversational agents or chatbots have shown promise as an alternative method to traditional and online surveys for data collection. In such applications, the agent converses with the user to collect data about predefined topics. They are becoming common in domains such as healthcare, e-commerce, and banking. In this work, we wanted to use chatbots for collecting rich and multifaceted public input during major societal crises such as COVID-19. In such circumstances, collecting rich and in-depth public input is essential for crafting appropriate plans and policies. Such societal crises require fast and timely data collection. The use of chatbots can speed up this process. However, such domains can be multifaceted and multiscalar, where we wanted to collect data at various levels, including how the individual has been impacted, including their mental health, impact on family, their relation to city and urban environment. The typical design of a chatbot for data collection is single agent, where a single chatbot agent converses with the user to collect data. For instance, if we designed a chatbot to collect data about the impact of COVID-19 on healthcare, household, and work of the residents of a small town, then a single agent will have conversation on all these topics. However, it is computationally expensive to train a single agent to converse on 3 different topics. And due to the presence of 3 different topics to converse on, the single agent could make mistakes in identifying the user's intent. This could lead to breaks in the conversation. A possible alternative is to design multiple agents, each of which talk to the user about a single topic. Prior research suggests that dividing the conversation between multiple agents can improve conversation flow and reduce conversation cost. However, data collection using a multi-agent chatbot is an emerging area with many open challenges and questions. What is the appropriate number of agents? How to handle turn-taking between different agents and topics? How the design of agents impact user experience and engagement? How does a multi-agent design compare to single agents in terms of data quality? To investigate these questions, in this work, we designed and developed a novel multi-agent chatbot platform, CommunityBots. We wanted to mimic how people talk to a group of experts, and therefore in CommunityBots, each chatbot acts as an expert in collecting data in one of the conversation facets from the public. To evaluate the use of multiple chatbots for collecting rich data across various topics, we used the COVID-19 pandemic as a testbed. The first step of designing this multi-agent chatbot was to determine the appropriate number of agents required to gather such multifaceted data. To answer this question, we conducted a within-subject Wizard of Oz pilot study where a member of the research team worked behind the scenes as an agent to respond to user messages. We used 3 design variants with 3, 4, and 5 chatbots. 18 university students participated in the study. The results from the pilot showed that 44.4% of the participants preferred 3 agents, and 33.3% mentioned that they did not have any particular preferences. Moreover, we discovered from the post-study questionnaire that the participants felt overwhelmed when conversing with a large number of chatbots. We had an initial set of 10 different conversation topics. Based on the results of our Wizard of Oz study, we categorized the conversation into 3 topics: household, work, and healthcare, and integrated 3 chatbots in CommunityBots, each designed to handle conversation in a specific topic. One of the open challenges in chatbots is handling topic switch, which is switching between different topics in an agent. An additional challenge for multi-agent design is chatbot switch, which is switching between different chatbots. To address these problems, we designed a conversation and topic switching mechanism. The CTM decides when to switch between topics in a chatbot. For example, switching from conversing about home office to work-related transportation. The CTM also decides when to switch between chatbots. For example, switching from household chatbot to work chatbot. The figure shows the web interface of CommunityBots. The interface consists of a chatbot panel, that contains information on the individual chatbots along with the topic of the conversation. Each chatbot has its individual avatar along with the current topic that it is conversing on. The active chatbot is shown with eyes open. The chatbot panel responds to topic switching and chatbot switching by providing visual feedbacks. The chat container shows the conversation history between the chatbot and the user. The users are provided with a text area to input their responses to CommunityBots. The navigation bar contains a link to a tutorial that contains instructions on how to interact with CommunityBots. In the design of the interface, we use visual indicators to mark active, chatbot, and conversation topic. We color-coded the agents and the speech bubbles, and used opening and closing of eyes to mark the active and inactive chatbot. Consider the following conversation scenario. The user is conversing with the household chatbot, which asks the user about their family life. The user responds with skip this topic. The natural language understanding module of CommunityBots processes the user input and determines their unwillingness to respond. This information is passed to the topic switch mechanism that determines the next conversation topic for household chatbot. The topic switch mechanism determines that the household chatbot has run out of topics and disables it. Next, the chatbot switch mechanism is activated, which enables the next available chatbot, in this case, the work chatbot. The user then proceeds to converse with the work chatbot. To evaluate the effectiveness of CommunityBots, we conducted a between-subject study with 100 crowd workers. We compared CommunityBots against a single agent baseline. The participants were randomly assigned to one of the two conditions. We measured and compared the response quality, user engagement, and conversational interruption between the two conditions. Specificity, relevance, clarity, informativeness for response quality, response length, expansiveness, and Likert scale responses from post-study questionnaire for user engagement. We define expansiveness as the voluntary willingness of a participant to respond with free text input on closed-ended chatbot question that only required a predefined response, such as a yes/no response. And interruption rate for conversation interruption. Interruption is defined as a signal in the participant's responses during the conversation that indicates their angry, uncomfortable, impatient, or confused intentions. Examples of such signals can be a user saying, "End the conversation." On average, the participants that interacted with CommunityBots provided specific, relevant, clear, and informative responses. In addition, the participants who interacted with CommunityBots also provided longer, more expansive responses. We performed Kruskal-Wallis test and found statistically significant differences in the specificity, response clarity, and expansiveness. The results from the post-study questionnaire suggest that the CommunityBots participants found the conversation more engaging, perceived the conversation length as just fine, did not feel impatient during the conversation, and were satisfied with their interaction in comparison to the single-agent baseline. We performed Mann-Whitney U-test on the ordinal Likert scale responses for perception of engagement level, conversation length, and satisfaction, and chi-squared test on the categorical data for the perception of impatience during the conversation. We found statistically significant differences in all of them except the satisfaction metric. We plot the interruption rate for every participant in single-agent chatbot and CommunityBots. The results suggest that the participants who converse with CommunityBots experience much fewer conversation interruption compared to the single-agent participants. In addition, the results from our post-study questionnaire showed that the 94% of the CommunityBots participants felt that the transition between the different topics were very clear or clear, and 79% of them showed high level of perceived clarity on chatbot switching, saying the transitions between the different chatbots was very clear or clear. Finally, we discussed how multi-agent chatbots, such as CommunityBots, can be effective for maintaining smoother conversation flow, how a community of chatbots can create a more human-like conversation, and highlight avenues for future work on the interface design for multi-agent chatbots. Thank you.